Hi, thanks for joining my talk. This is the last talk in Black Asia this year. I'm Jinbum, who is working for Samsung Research and Samsung Mobile Security. Today, I'll be talking about taking kernel hardening to the next level. So let's begin with a brief introduction of today's talk. We'll focus on how to secure today's OS kernels. Particularly, we focus on two well-studied defenses, CFI and UAF defense, and how to take both of them to the next level. This is an overview of CFI. We only deal with kernel CFI that they utilize ARM pointer authentication. That is the latest security feature ARM present. And I first introduce what the problems are in more detail by demystifying the state-of-the-art solutions, including iOS kernel CFI. And then I'll introduce our new approach called PAL. There is an academic paper planned to appear at Using Security this year. And as for our second topic, UAF, I'll first explain on existing approaches and why they are not scalable up to OS kernels. And then I'll introduce our new approach called VIC. This is another academic paper that is published at SPLOS this year. So let's move on to the first topic, pointer authentication-based kernel CFI. I will give you a brief information for background. So CFI aims to enforce indirect branches jump to only valid destinations. For example, we have three functions here, and in original CFI, this function pointer is only allowed to go their function entries. So we can say that allowed target is 3 in original CFI. And if you take into account the function pointer type, which is known as type-based CFI, FPTR function pointer is not allowed to go function 3 because the type of function 3 void int is not different from different from the function pointer type int. So allowed targets in type-based CFI decreases by 1 compared to original CFI. So with this simple comparison between original and type-based CFI, we can get to know two things. First, low allowed targets means a strong security, and context is a key to lower allowed targets. This means that if we use another value as a context other than function pointer type, allowed targets can get even lowered. So this is how type-based CFI can be implemented on top of ARM pointer authentication. When generating a function pointer, there's a newly added instruction PACIA executed. This instruction takes as input a pointer and a context that can be hash of the function pointer type in type-based CFI. This instruction goes through a lightweight block cipher named Quarma inside hardware, which signs the given pointer with the given context and key that serves as a secret. And its outcome will look like a pointer that contains method authentication code. This code is called PAC, pointer authentication code. And this PAC will be stored in the unused bit of a pointer like this. We call this pointer signed pointer. And then when the signed pointer is used, there is another new instruction named AUTIA, which authenticates the signed pointer with the given context. If both of context and key match, the PAC in the unused bit will be restored to the original bit, what we call low pointer. So this low pointer can be used without any trouble. Okay, let's see what happens if a context mismatch occurred. This case represents when attack happens. It signs with the type of void int, but authenticates it with int. So in this case, the PAC in the unused bits will transform into an unpredictable one that is completely different from the original bit. So a system goes down when this abnormal pointer is used. So this is how PA detects pointer modifications and guarantees security. Okay, let's see the first pain point. The current kernel CFI systems have a low CFI security. As I mentioned earlier, what context to use would directly relate to security and comparability of CFI system. So we use two factors as a basis to evaluate how good a context is. First, a more unique a context is, a more secure a CFI system will be. Second, context is invariant. It likely has no compatibility issue. So building a secure and reliable CFI kernel system comes down to a problem of figuring out the best context in considering these two aspects. The most widely adopted kernel CFI is a type-based CFI we discussed earlier slide. We can make a reasonable guess on why in considering its context, the function pointer type. Actually, the function pointer type is not that much unique because there are lots of function pointers that share the same type. So several attacks have demonstrated it can be broken. But it is totally invariant because the function pointer type can be determined at build time and is guaranteed not being modified at runtime. So it has no compatibility issue. Since many of commodity OS kernels prioritize compatibility over security, it's understandable to go for type-based CFI. Okay, iOS kernel CFI goes one step further by using a better context. As you know, iOS kernel is made of different languages. They use a better context for C++ and Objective-C, but not for C. This is why iOS kernel CFI is not directly applicable to other C-based OS kernel, such as Linux or FreeBSD. I will detail why they do nothing for C function pointers later. Okay, let's look at how iOS CFI protects C++ function pointers, V-table entries. Interestingly, they use a combination of dynamic and static context, storage address, and hash of function name. For example, we have an obj A of class A, which is located at A00 address. And function 1, that is one of member functions, is signed with 800 storage address and hash of function name as a context. So function 2 does likewise. Okay, let's evaluate how this context is good in the two aspects that I mentioned earlier. The first, hash of function name is unique within a class. So signed function 2 pointer cannot be used for function 1 and vice versa. And this is invariant because it is a static value. So it looks perfect. But second, storage address is also unique within an address system. So signed function pointer at A00 address cannot be used for another address. But this is not invariant because a certain address can be freed and reallocated to another object. So you may remember that I mentioned using not invariant value as a context may cause a compatibility issue. So I will show you what problem could come up in reality in next slide. Actually, a problem can arise when it comes to protecting C function pointers. Here we have a simple function that contains memcopy, and there are two pointers of struct obj, destination and source, and their function pointers are signed with corresponding storage address as context. And then after memcopy, destination's function pointer will be identical to source's function pointer that is signed with source's storage address. Finally, when destination's function pointer is used, of course, it takes the destination storage address as context, but obviously there will be context mismatch occurring because the actual destination's function pointer is signed with source's storage address. Basically, this is because a context, a storage address is not copied along with a function pointer in memcopy. Okay, with this example, we can get to know that a dynamic context would break compatibility in memory-related functions that are very commonplace in OS kernels. So this is why iOS decided to leave C function pointers unprotected. Okay, here is the takeaways. The use of static context solely is not as secure. So iOS uses a combination of dynamic and static context, which promises a better security. But use of dynamic context is likely prone to compatibility issues, especially in C-based OS kernels, Linux, for example. So the next thing we have to do is to figure out the new context to improve security while preserving compatibility. Okay, to this end, we propose a new combination of context. We newly propose a combination of 2 static contexts and 2 dynamic contexts. Among other things, obj bind plays the most crucial role in our system. So I focus on describing what obj bind is and its implication. First, our baseline context is identical to that of type-based CFI. In this example of struct IIQ action in Linux, to sign handler, we take its type IIQ handler T as the first context. On top of that, we use the type of an object, struct IIQ action in this example, which contains a target function pointer. This can enhance CFI precision a lot because lots of function pointer in OS kernels are used along with its object type, as you can see in function 1. Okay, next, this is a dynamic context, what we call obj bind. It blends a certain field value into a context. What field to use is up to developers. For example, if we choose the name field for obj bind, the field value, the address of O1, will be taken and used in signing instruction. So finally, these 3 different contexts are going to be securely mixed and used in signing instruction. Okay, so far I've been saying about what obj bind is, not why obj bind is good, and how it can solve the problem iOS kernel CFI has. So from this slide, I'll talk about what motivates the need of obj bind and its implication to highlight the benefit from obj bind. Actually, during our research ongoing, we found several OS design patterns beneficial for CFI system. That is, a lot of struct has a field that is unique as well as invariant. Obj bind is meant to target such a field. So I'll explain on why obj bind is unique. For example, the name field in IIQ action most likely differently initialized for different codes. Function 1 sets O1 to the name field, but another function most likely sets another value to the same field. In other words, this name field serves as a unique identifier for different instances of the same object type. So the signed handler of name O1 cannot be used for the signed pointer of O2 name. So we found this is a very common pattern shared across from Linux to FreeBSD. So next, obj bind is invariant. A unique field in an object is most likely defined as const value. There is a symbol for invariant. So this is initialized at the time of object creation and is not changed until it's freed. So we can say that it's easy to maintain and it's not involved in compatibility issues. Because if it's not invariant value, we have to reassign a function pointer whenever the field value changes. But with this kind of invariant field, we don't need to care about such a reassigning. Okay, lastly, let's revisit the problematic memcopy example, but with obj bind. We have a similar code. It has 2 pointers, destination and source, but their handlers are assigned with corresponding name field as context. Of course, they have different names, destination and source. Okay, after memcopy, destination's handler will be identical to source's handler that is signed with source's name. Finally, when destination's handler is used, it takes the destination's name that is identical to source's name as a context. So there will be no context mismatch and no compatibility issue happening. This is because our context, the name field, is copied along with an associated handler in memcopy function. In conclusion, obj bind can enhance CFI precision while still being compatible to memcopy functions. Well, let's see the security enhancement of our method. We applied our solution to Linux and also applied obj bind to 87 structs that are used the most throughout the Linux. Note that part is a PA-based, type-based CFI implementation that comes from an academia. For comparison, we counted the number of indirect calls that share the same context. If it's shared for less than 5 places, we treat this secure. And if it's shared for more than 100 indirect calls, we treat this insecure. And this percent indicates how much each case accounts for of our context. Okay, you can see part has the smallest number of secure context. It's because part is the only thing that doesn't use a dynamic context. And iOS shows a decent number of secure context because it uses a storage address as a context. But it leaves a large attack surface that has 6,000 indirect calls sharing the same context, because they use the same context for all C function pointers. But with PAL, most of contexts are not shared in more than 5 places and 0% in insecure context. Okay, for performance evaluation, we made a PA-enabled Linux that can be running on M1 chip of Apple, and install this Linux into the latest Mac Mini that supports PA. As a result, we observe from 3 to 7% in post. Okay, let's sum up this section. A kernel CFI can make use of OS design patterns to enhance CFI security without compatibility issues. So, but to be honest, use of good context is not the only thing needed to build a secure kernel CFI system. There are other things that must be addressed, but were not discussed today. To check them all, I recommend you read our full paper. Okay, let's move on to the next pain point. In the previous section, we discussed on a matter of kernel CFI rather than on PA itself. In this session, I will focus on the security problem of PA itself. That is, a complex compiler behavior can introduce subtle bugs that are hard to detect. This is a pipeline producing PA-enabled kernel. This rectangle in the middle of the slide represents a modern compiler framework, LLVM, for example. And this framework takes kernel code as input, and it goes through 3 different phases: front-end, IR, intermediate representation layer, and ARM6 for backend. If you want to add a new function into this core compiler framework, the most common way is to write your own path or write your own compiler plugin and attach it to the IR layer, like this. So PA path here means a compiler plugin that inserts security checks for pointer authentication. Okay, let's see an ideal flow of how kernel binary is produced. We have a simple C code generating a function pointer to function 2. And it breaks into 2 IR instructions that this IR layer can recognize. And our PA path takes this as input. And our path interposes a signing instruction between these 2. So finally, it transforms into ARM6 for assembly by going through ARM6 for backend. In an ideal situation, as you can see, the II code perfectly match with the final kernel binary. But in reality, the II code our PA pass produce would pass through other compiler passes that are out of our hands, which result in an undesirable kernel binary. For example, there will be unexpected instructions between what we intend. Question marks here, and it can be any form of instructions. Let's look at why and how it will be problematic. Let me clarify our threat model first. We assume attackers can corrupt memory, but not registers. In this secure sequence, L1 loads the address of function 2 into X1 register, but X1 never spills onto memory, and is stored onto memory as a signed form always. So we can say for sure it's secure in our threat model. Okay, but in reality, there are 3 more instructions can be added. For example, due to a complex compiler behavior from L2 to L4, L2 stores the low pointer onto the stack memory and assume stack vulnerability exists in L3, then attackers can put an arbitrary pointer onto the stack memory. And then L4 and L5 would load and assign the attacker chosen pointer. By exploiting this sequence, attackers can make an arbitrarily signed pointer. This sequence is called signing oracle. Okay, here is the takeaway. Modern compiler frameworks are so complicated that subtle bugs can arise, and attackers can disarm CFI defenses by exploiting such bugs. Okay, to solve this problem, we propose what we call static validator. We define 4 principles that the final kernel binary must respect for security. This validator checks these 4 principles by performing a binary level static analysis on a whole kernel binary, but in the scope of interrupt function. We ran this validator on 3 different kernel binaries, iOS and Linux compiled by Purge, and Linux compiled by our PA pass. There are 4 principles we predefined. I'll explain on each of them in next slide. Okay, before looking at the first example of violation, I'd like to explain on a template used in saying about violations we found. You can see a secure sequence on the left side and an insecure sequence on the right side, which is an actual violation we found. Well, first case is a case of absence of PA instructions. This function takes X0 register, this is a pointer, and loads a function pointer from the given pointer and authenticates and uses the function pointer. This is the secure sequence, but in the real binary, we have several cases that have no authentication instructions. So we are suspecting that this is an implementation bug of compiler pass. Next one is a simple function that calls a function pointer pass through a function parameter. So this takes as input a function assigned function pointer and authenticates the function pointer and uses the function pointer. But in the real binary, there was a spill to the stack memory and L2 immediately after authentication. As I mentioned earlier, after authentication, X2 register will transform into the low pointer. So L2 stores the low pointer onto the stack memory. Then by corrupting the pointer on stack, attackers can make it jump to anywhere from L4. This is what we call TOC/TOU problem, time of check and time of use, because the point of check L1 is not adjacent to the point of use L4. Okay, this example is a secure signing code that loads address into X21 register and signs it in place. But in the real binary, an address to be signed comes from the X2 register that is one of function parameters. This means that if attackers can control this function parameter, they can make an arbitrarily signed pointer by using this sequence. This is an instance of signing oracle. Okay, let's see one more example of signing oracle. There was a function call intervened between these two instructions. Okay, it seems no problem at the first glance, but it's definitely problematic because there are a lot of instructions to execute in the call function. I will go in more detail. L1 here loads an address into X22 register. That is one of coldly saved register in ARM64 architecture. This is the T. Then the coldly function is first to store the X22 register, the coldly saved register, onto the stack memory. Because this is what the coldly function has to do in the view of compiler and CPU architecture. So this example also falls into a signing oracle problem. Okay, we found several violations on all of those binaries, but it's worth noting that violation does not mean exploitable because there are many variables involved in exploitation. For example, the interfunction binary analysis that is out of scope for now. Okay, here is takeaways. We should trust a binary level validator instead of a complex compiler. And we believe a major Linux vendor can incorporate this validator into kernel development lifecycle to make sure their kernel release is completely secure. Okay, let's move on to the next topic, user FTP defense. Okay, the main problem here is that no one cares about kernel UAF defenses. Okay, this is mainly because of two things. First, OS kernel is huge in size. And second, kernel is in most cases the lowest level software that is not managed by another software in more depth. So to understand what the problems are in more detail, we will go over existing approaches and why they're not scalable up to OS kernels. So first approach is called pointer invalidation, which aims to make no dangling pointer by precisely tracking the reference count of object. C++ has a mechanism known as smart pointer. This is similar to IRC and ARC in Rust. This can be realized by a special class, shared PTR, for example. If developers code a pointer as a smart pointer, its reference count gets recorded as 1. And when a pointer copy happens, the reference count will increase this by 1. And when this function ends, the reference count will drop to 0, and naturally the object will be deallocated because there is no reference to the object. As you can see, there is no possibility for dangling pointer, but the thing is, to take advantages of this approach, developers have to turn all pointers into smart pointers, which is unrealistic in terms of engineering efforts. To tackle this problem, researchers proposed an automatic solution. They designed a new compiler path that analyzes source code and interposes on all memory allocations and all pointer copy operations to automatically manage reference counts without having to use smart pointers. However, this automation comes with a new problem. For example, we have a casting operation here from pointer to integer. Okay, how should we deal with it? This is an obvious pointer copy operation in some sense, but it's not in other sense. Should we increment a count or not? It's hard to determine which one is correct behavior because it depends on application-specific semantics. This wouldn't be a big problem in user space application because developers can find all of such cases and fix them by hand manually. But this is an unrealistic way in OS kernels because OS kernels are huge in size. Second approach is to simply never allow reallocation. Some of you may think this doesn't make sense, but it does in practice for user space application due to the large size of virtual memory, 64-bit to be exact. But when it comes to OS kernels, this wouldn't work because a kernel memory allocation directly takes up part of physical memory that is much smaller than a virtual memory. So this brings out of memory issues very quickly. This is mainly because of the fact that OS kernel memory is not managed by anyone in more depth. So last one is called access validation that checks if a pointer dereference is valid. In this approach, when memory allocation happens, it generates random ID, and this ID is given to two different places. First, this is going to be stored in the unused bit of a pointer as AMPA does. We call this pointer side ID. And second, this is stored in a separate table that is kind of key value storage, where key is object address and value is random ID. We call this object side ID. So finally, when a pointer is dereferenced, it compares if the two IDs are same. The problem is every pointer dereference demands additional memory accesses to locate and read object side ID. Typically, 3 additional memory accesses needed. So it brings on substantial performance overhead. This is because the implementation of this mapping table looks like a multi-level page table where the level is 3 in general. Okay, so far we got to know why they're not scalable up to OS kernels. Of these 3 approaches, we decided to go and optimize the access validation approach because we believe there is still room for optimization in that approach. So it's time to explain on what we did to optimize access validation approach. So our objective is to have only one memory access needed to obtain an object ID. So I'd like to introduce the first attempt we did, which ended in failure actually. We kept the pointer side ID as it is, but we moved the object side ID to the start of the object instead of maintaining a separate table. In this setting, when this pointer is accessed, the pointer -8 always points to the start of the object ID. So you can see everything can be done in just one memory access. But there was another problem occurring in ID lookup for the middle of a pointer. Okay, say that we have another pointer that get P2 that gets the middle of this object. And when this middle pointer is accessed, the pointer -8 will still point to the middle of this object, which results in an incorrect ID lookup. So the next thing we need to do is to get around this problem. Okay, we came up with base identifier to resolve this issue. Before, the random ID was the only thing that places in an unused bit, but we divided it into 2 different parts, base identifier and random ID, and dedicate k bit to base identifier to hold information for locating object ID. Before getting into how it works altogether, I'd like to explain 2 assumptions necessary in our system. We have a 4 kilobyte region. This is our first assumption. Every object is remitted up to 4 kilobyte in size. And this region is divided into multiple slots where each slot is 64 bytes in size. This is our second assumption. That is, every object is aligned with 64 bytes. And base identifier is put to use to certain slot index. So of course, such size limitation can be adjusted for the need of developers. But there is one trade-off in these 2 assumptions. Let's take another memory alignment for assumption 2 and see what happens. Now we take 16 bytes alignment instead of 64 bytes. It can bring a less memory overhead to our system, but consequently, there will be more number of slots demanding a larger bit of base identifier, 8 bit to be exact. Then the capacity of random ID will decrease by 2 bit accordingly because we have only 16 bit to accommodate both base identifier and random ID. As a result, it gets a lower security because the random ID indicates security entropy. So in our system, developers have to take a responsibility of configuring this trade-off based upon their need. Anyway, we recommend using 4 kilobyte and 64 byte by default. Okay, let's see an actual example of how it works altogether. Suppose that this is a 90 bytes allocation, and we first force this allocation 64 bytes aligned. So we assign 128 bytes for this allocation and put the start slot number 4 in base identifier. This is where the object ID is located. Okay, next it gets the middle pointer. As you can see, BI is still preserved, but while pointers altered to point to the middle. Finally, when this middle pointer is accessed, we try to locate the object ID by using both base identifier and pointer. We first do masking with the pointer with 4 kilobytes. That is the maximum size in our assumption, and its outcome would be slot 0 address. And then we add a multiplication of 64 and the base identifier 4. This is slot index. As a result, we can obtain the location of object ID correctly. There is no additional memory access needed in locating object ID. Everything can be done in just one memory access. Okay, we evaluate our solution on 2 different kernels, Ubuntu and Android, on 2 different CPUs, x86 and ARM64. They are imposed an overhead of around 20%. To be honest, many of you may still think 20% is still high in real-world system. So we also developed a performance-first variant using ARM top byte ignore feature. With this way, its performance reduces down to 1 or 2% overhead, but its security gets lower alongside, as being not able to inspect the middle pointer. So in this setting, we are only able to the start pointer of an object. Okay, my presentation ended. I can take any questions from audience now. Okay, thanks for attending my session. And if you have any question, please contact me on Swapcard or email, please. Thank you. Thank you, everyone.